screen. Share screen. Now I'm sharing my screen, so can you see my screen clearly?
Yes, it's very
okay.
Thank you.
Thanks. Okay. Hello everyone. My name is Chen. It's good to have this chance to introduce my work in your group meeting. So very glad to show you some of my work related to energy systems. So my topic today is AI-driven energy design for energy systems. So AI is a very big topic, right? So actually, this presentation is about my one of my published paper. So AI is a big topic. So in this paper, I'm going to employ a swarm algorithms, which include there is a few swarm algorithms in the AI, which is AI sub branch. So in this talk, we're going to employ the swarm algorithms as the AI tool to perform the engineering design and perform the optimization for the energy system. So this is about me as a link to my excuse me, university page. My research interests include artificial intelligence and its cross-disciplinary applications. Because my background is engineering background, but the AI as a tool, I have a few applications in not only the mechanical engineering, EE engineering, chemical science, but also in the social science as well, such as social science and exchange rate modeling things, something like that. So AI and its applications. And the second one is Industry 4.0, which is my real background. So Industry 4.0, digital twin, and digital manufacturing also use AI as a design tool. The third one, robotics and autonomous systems. I have a few projects in this area, which is robotics, is a very big area as well. So I will take the hummingbird-like robot as a case study to introduce my background in the later slides. And the first one, data analytics. So also, I have AI as a tool, and I'll have a big data from the applications, and that's why we can have a cross-disciplinary application and the collaborations. So the contents for today's presentation is, first of all, I'd like to introduce the AI tool, which is called Computational Intelligence Aided Design. It's short for CIAD. So you just consider it as an AI tool. Now, second one is modeling for the electricity consumption. The third one is the specific swarm algorithm, which is called Firefly algorithms. And the fourth one is we introduced two trending index to assess the evolutionary performance of the overall optimization. The next one is simulation results, and finally conclusion and the future work. The first one, something about the AI tool. Now, for industrial product design, generally it has several steps. So as shown in this picture, we have 7 blocks, which means 7 steps for a product design. Basically, it's CIAD. CIAD, by the way, CIAD is short for Computational Intelligence Aided Design. So we everyone knows CAD, right? That's computer aided design. So in here, we try to involve or embed the AI as a tool. So CI means in computational intelligence. So CID means we have AI driven CID here. So CID, CAE, engineering, it's a design. First block is design. Second block is engineering analysis. And third one is VP, virtual prototype. We build a virtual prototype and then move on to step number 4. When we have the modeling or design in computer, a virtual prototype, then when we have the optimized design, now it's time to build our physical prototype in block number 4 by using 3D printing technologies or other fast prototyping technologies, and then move on to CAM. AM means manufacturing. So AI supported manufacturing. Then move on to number 6, system integration and test and installation, and then number 7, applications to the end user. So this framework has been submitted to ISO Artificial Intelligence Subcommittee as a use case. Now, we have a general framework for the CID. Now, this slide shows the concept, the conceptual framework is not good enough for end user or engineers how to use it as a tool. Now, in this slide shows CID implementations. This is how we build the CID design systems. We have 8 blocks in this picture. As you can see, block number 1 is AI itself. So we develop new AI algorithms. We test AI platforms. So we do AI things in this block using the RD tools such like MATLAB, C++, Java, Python, something like that. And then we have a big block number 5. Block number 5 digital prototype includes the CAD, CAE, and the virtual prototype in number 3, number 2, 3, 4, or link to block 1, which is AI, which means in digital prototype, all steps supported by the AI or driven by AI. Now move on to block number 6. We will just try to show using the VR or AR technology to show the end user and or the engineer how the AI can perform the optimization in real time. Using the VR or AR technologies, a designer can see how their modeling or their product, how the algorithms can improve the performance of their product. Something like the right hand side 2 photos as the animation. You can see there's when the modeling is when the block is moving, you can see a different color in the different part, which shows different reactions to the animation. So we'll move on to the block number 7, which is physical prototype. We have well-designed virtual modeling at hand, then we can build our physical prototype. Now, we have block number 8 to support all the blocks above. HPC means high performance computing. So all the AI algorithms, all the simulation, all the optimization requires high performance computing to support it. Let's move on to the next slide. Let's put it in a bigger picture, which is the left-hand side block, which is the one from the previous slides, which can be linked to the going down to the block number 9, which is big data and cloud from industry or real applications, and move on to the right-hand side up to number 10, the 11, and the 12. You can see move on to digital manufacturing, and move on to a few robotics applications and future steps in block 12. And this block, this design framework is for industry product design. So you can see a few product design here. So now how to use the AI tool in a energy section. So we don't really need CAD, CAE, and the virtual prototype for every applications. In energy modeling, which have a simpler version, which is block number 1. We have the modeling, right? We have a model at hand with parameters controlled the model, and number 2, move on to the optimal design, supported by the block number 3. The CI integral solver means a set of artificial intelligence algorithms, which you can think it as just AI algorithms. And then we can move on to excuse me, move on to block number 5. When go around a few loops, and validation in block number 4. When the result is yes, the results meet the design criteria, then we move on to the results. We have the results, then we move on to the post-processing, like data result visualization and technical report generation, something like that. Now, this framework is a simple version of CID for the energy modeling. So I'm going to the following steps, the following blocks, parts. I'm going to show how I just employ the CID framework in electricity consumption modeling. Now we have the modeling here, which is mathematically expression, right? Controlled by a few parameters here. Yeah. So energy EC is the estimation of annual national electricity consumption. So the EC is electricity consumption. So right hand side is mathematically expression given by as a list down here. So controlled, as you can see, controlled by a few parameters here. All the now with the expression at hand, right? This is an expression for energy electricity consumption. Now we're going to build our fitness function. Fitness function is like you can think of it as an objective function for design. So in here, we're trying to maximize the error, actually is the RMS is root mean square. Put it in index. This index is called MMAP. We're going to talk to more about it. So it's actually a trend index. We're trying to this fitness. We're trying to maximize the root mean square of the error. But with as you can see, with a minus in front of RMS. So we try to, which means we try to build a arrow fitness function and maximize the expression here which is indeed to minimize the error as a design objective mathematically. Now, Firefly algorithms, which is a type of swarm algorithm, which inspired by the Firefly. The flow charts as shown in the slides. It's a lot of text. So to summarize these algorithms, which is now we have a group of Firefly, right? Now to animate their behaviors, they will try to update their status in accordingly to the environment change, right? So we have time t. Every Firefly individual have its individual status. Then time t plus 1, and the status will update accordingly by reacting to the environment change. So in this way, they all the Firefly will go to the a place where have most density of the food. So we're chasing the food, though we have higher food density, we have more Firefly there. So that's it's a that's a social behavior. The algorithm is going to find the place where have the food for everyone, most food for everyone. Now this is the link. I put it on the MATLAB's MathWorks website. Everyone can download it. So we have the AI, the Firefly algorithm as a tool. Now, right-hand side, briefly, we have steps to prepare our data for our electricity consumption modeling and analysis. Now we have a raw data. In this modeling, we prepare our data from all data comes from public data. So from yearbook and data resource, all open to everyone. And second step, we're going to perform the data handling, pre-handling, and normalization. And third step, we build our electricity consumption modeling and its fitness function. In the fourth step, prepare for its optimization. Now we have introduced the two trend index. So index is try to show the performance of the overall optimization. Now we call it MMAP, which is moving average of the mean value, and moving average of the standard SCD. It's a wide used statistics index. So we have a moving average, means we capture the evolutionary process. We capture the data during their optimization. So we can see the curve in the right-hand side looks like move smoothly, yes, goes smoothly. Now simulation and results. To prepare the simulation, we have a list of parameters settings here, right? According to our prepare to real application and our previous experience, we set a few parameters here. Now this is Firefly algorithms is a kind of evolutionary computing algorithms, which means it's controlled by the evolution generations. So the x-axis is generation. We set it to the 100 generation. So max generation is 100. So we stop here when simulation goes up to the 100. As you can see, the curve goes up very quickly, almost goes to a steady status is within 10 generation, which means the algorithms perform very well with a high efficiency and very steady results. And left hand side is MMAP with SDD. SDD you can shows in the middle is MMAP in the dot curve. Left hand side dot curve is the MMSCD. It's described the evolutionary range of this optimal design. And right hand side is the MMSCD. You can see it's go down very quickly and steady, which means it's very stable, and we're going to converge to the steady status very quickly. Now, and the results right hand and left hand side is the easy approximation, and we can see by our own eye, and that there's the circle is the real data from a public yearbook or something like public data, and the red solid line is the mean of the series. Series means the result from our EC modeling. If you still remember, the EC equals something like that, something. It's a mathematical expression. So as we can see by our eye, it goes very closely. Now, and on the right hand side, we try to plot the error between the real data and the theory data modeling. As you can see, it's quite almost within stays within the 10% plus or minus, which is almost acceptable. Now this is this table gives the prediction results and explanation, and down here we try to plot 3D results, which is we call it data visualization, to show how the results going, how the 3 different parameters interaction to each other. Now, conclusions and the future works. Concluding, and so our modeling is has a good agreement with actually conception data. So you can see the error is small, and the real data and the modeling curve stay very closely. And we're going to build a more complex modeling with more parameters in it to show. We will try to involve the GDP growth, GDP data in the next version of the electricity consumption, to provide, which can provide suggestions to the decision maker how they are going to plan their energy policies. Right. Now, future work, and as you can see, we in this paper we try to use only one Firefly algorithms. So if you still remember, I mentioned there is a CI integrated solver, which means we try to integrate a lot of a set of algorithms in one solver. So to provide the end user don't need to know the details of algorithms for the end user, or policymakers, and they just need to think it as a calculator, or you just give input and help you to perform the optimization and to generate the output and just suggestions to you. It's easy to use platform, and also to validate, try to because currently in this paper we have a mathematical expression to build our model. So in the future, We try to build a model by the algorithms using the data, using just data. So this model is not only in this polynomial form of expression. It could be in other kind of form to fit the data. So the data-driven design modeling will be our next step of work. So and then we try to involve the real data and try to compare the new model with the real data to provide more accuracy estimation. So that's the next future work. Now reference to the first one to the paper, a second one to the book, and introduce a few algorithms in it. Now this is last slide of my presentation, and thanks for the time and any questions.
So thank you very much, Leo, for this presentation. I will now allow anyone, if you guys have any questions, to ask Leo.
Do you need me to still share my screen, which would be easier for everyone to record the slides?
Yeah, if you want, you can. Yeah, you can keep the slides. In the meantime, as I do have a questions I can see currently. I cannot see at this point, at least, any hands being raised.
Yeah.
So my question is, if you can elaborate a bit more on this Firefly algorithm that you described in the beginning. If you can say, if you can say when is this used and if it is used to solve what type of problems?
Now, and you can consider Firefly algorithm is an algorithm inspired by the social behavior of Firefly. So you can consider it as just a design tool, as your calculator for your if you have your modeling at hand for your problem. With you have your problem, you have the mathematically expression as input for input for the Firefly algorithms as a calculator. So just use it as a calculator. You have your input data, and then it will generate the output for you. So for AI, actually for the end user, we have a discipline, different background. We have different works research to do. So you don't have to understand every algorithms in your work. You just use it as a tool for your problems. Will that be easier to explain what's the AI tool and the Firefly algorithms? So if you want to know more details, you can see the flow chart and the codes, pseudo codes. It gives the detail. If you from a computer science background, you can see the algorithms steps very clearly. It goes to the different loop initially. Well, in the when you begin the algorithms, you will set an initial parameters for every parameters in your modeling and your algorithms, and then it goes while means when you set the termination condition, which is all most of the time it's a max generation, which is that 100 in our simulation. So when the generation goes to the 100, the simulation will stop. So before that, it goes to by the population, which you can see there are two for loop here. So which means the algorithms will go through the population one by one the algorithm will go through Firefly, every individual Firefly to check its status. So to keep the good result and remove the poor results. So in finally, we'll keep all the better results compared with the previous generation, and keep it to the final, which is becomes the best solution within your 100 max generation. So that's a general idea of the Firefly algorithm, which is also the general idea of computational intelligence, which is the main branch of the AI. Yeah.
Thank you very much, Leo. So we have a question from Elias. So Elias, go on.
Yep.
Yeah, thanks, Natalia. Thanks, Leo, for the presentation. That was very interesting. I wanted to ask a basic question in the beginning. Is this algorithm used for optimization or prediction? I mean, that's a basic question to ask.
I'm sorry, I didn't catch your question. So your algorithms,
in your method, I mean, this paper is for electricity consumption optimization or prediction?
It's a prediction, yes.
Prediction, okay. But so you use optimization in order to do prediction, right?
So yeah, we have our model. We have a modeling here. We have our data here. So we take a part of the data to train our modeling, which means to the first half data we perform the optimization to select the best parameters to fit the real data. The second half, now we test the modeling to see if the optimized modeling can take as a prediction tool for the future. So
I understand. I understand now.
Yeah.
Nice. Yeah. Thanks for this. And also, have you tried other algorithms for this problem? I mean, other heuristic optimization algorithms. For example, you mentioned GA for future work. I mean, for this work, have you tried others?
For this problem, for this paper's problem, I tried only Firefly algorithms here. So I did have a lot of few other algorithms, but they are applied to a few different other questions.
Yeah.
So
okay.
Yeah, we'll try.
Yeah. Nice. Okay. Thank you very much.
Yeah, as you can see, sorry. As you can see, the results goes very quickly to a steady status, which means either this question or this model, this problem is very simple. It is too simple to the algorithm, or the algorithm is has its high performance,
right.
very efficiency.
Yeah, I understand. Yeah, nice. Yeah, thanks, Leo.
Yeah, no problem.
Thanks, Elias. So do we have any other questions for Leo or comments? Great. Okay, I can see. Elias, did you raise your hand again? Sorry.
Yeah. Sorry.
Okay.
I mean,
I thought I made a mistake. Okay, go.
Yeah,
go
if there
on,
are
Elias.
no questions, I mean, I can ask one more if that's okay.
Yeah, of course.
No problem.
Okay. Yeah. Actually, you mentioned multi-objective optimization in the end using genetic algorithm, for example.
Yeah.
So what other objectives, I mean, could you consider here?
It's very depends on the how many objectives do you have. Some as you know, we have the objective. You have two objectives. It can be called multi-objective, right?
Yeah.
So if the objective is more than three, it's also called many objective. So in the real application, you cannot have too many objectives, right?
Yeah.
But But if you want to test the algorithms or test the theory, so you can try more than 10 objectives. But for the algorithms, it's different from the modeling and the algorithms itself, right? So
Yeah.
you can have as many objectives in your modeling, right?
Yeah.
So that's modeling from different applications. But for algorithms, there will be a few algorithms for the MO. I mean, multi objectives. You can try anyway, but if you have too many, it generally will not be very high efficiency. No.
Ah, okay. So you wouldn't
Yeah.
recommend having too many
So
objectives.
I won't suggest you for your real-time application or your real problem, you have too many objectives. But for your if you want to if you want to publish the academic research paper, maybe the reviewer likes to see how many your algorithms can try.
All right.
Yeah, the research
Right.
level. Okay, thanks.
Yeah.
Leo,
Thanks.
just to be, sorry, Elias, just to
Yeah.
be
Yeah.
mindful, Leo, that we're still recording. I'm saying because you've shared your screen, maybe you're happy with that. I'm just reminding, as I said in the beginning, that we're still recording, just to be mindful of that. Great. So thank you very much, Elias, for these questions as well. I don't know if anyone else would like to ask anything else to Leo or any other comments. Great. Then, as I said, because we are recording this, we will share the link for anyone that wants to see the presentation again.
Yes,
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 thank
no
you very
problem
much.
at
Sure.
all.
So
Yes,
for now,
yes.
yes. So for now, I'll stop the recording for now.